Hello, today we're going to talk about kinetic molecular theory. So kinetic molecular theory technically has four parts to it. The first part is that gas particles are extremely small compared to the size of their container. So I'm going to try to illustrate some of these, but the gas particles are very tiny and there's a lot of space in between them. So essentially the volume of the gas particles themselves is negligible when you're looking at the volume of the entire container. The second thing that you need to know is that the particles in a gas are in constant rapid random motion. So they are moving fast and they're moving randomly all over different directions wherever they want to go. A third assumption of kinetic molecular theory is that you assume that there's no attractions between particles. So none of that. Is this actually true and accurate? No, but it's a good assumption to make when we're talking about kinetic molecular theory because of the rapid random motion causing those attractions to be very, very small, very weak, not happening very frequently. And then the fourth part of kinetic molecular theory is that the temperature of a particular gas will be, or any substance really, is directly proportional to the average kinetic energy of that sample. So that means if you increase the average kinetic energy, you're increasing the temperature and vice versa. The faster the particles are moving, the higher the temperature that you're measuring and so forth. You should know that, well, you don't need to know this equation per se, but kinetic energy equals 1/2 mv squared. That's a mv squared. So it has to do with both the mass and the velocity, or the speed of the particle. So if you have more kinetic energy, the particles are moving faster. But it's not a perfect one-to-one because it also depends on the mass. So it really, whatever gas you have is going to react a little bit differently from there. So yeah, those are the four parts to kinetic molecular theory. And don't forget that anytime a particle of a gas is colliding with the walls of the container, that is contributing to the pressure inside that container. And the more collisions, the more pressure. So that means when you have a higher temperature, you're going to have a higher pressure inside the container. Remember that pressure and temperature are directly related, but it's because at a higher temperature, they have a higher kinetic energy, so they're moving faster, which has two parts to that. And this comes up relatively frequently on the AP Chemistry exam. Higher temperature, they're moving faster, so they collide with more force and with more frequency. So two parts there, force and frequency. Both of those things contribute to the increased pressure at higher temperatures. All right, so now that we kind of have an idea of what the kinetic molecular theory is, let's look at how we kind of quantify that. We use something called a Maxwell-Boltzmann distribution curve. And what that means is that, so it's a graph, okay, and it's a curve, and the area under the curve is telling you the number of particles. Okay. This is speed. And this is number of molecules. All right. Now, if you were to increase the temperature, the graph would change to look something more like this. Okay. Where the particles are going faster on average. So really look at the peak here versus the peak of the second graph. At a higher temperature, they're going faster, but you still have the same number of particles, they're just spread out more, okay? And it doesn't mean that all of them are suddenly moving faster. It means on average, they're moving faster. So you still have some down here in the very cold end and some down here in the very warm end based on their speed. Same idea if you're going backwards from that. If you decrease the temperature, your graph will look something more like this. So on average, the speed will be lower because it's at a lower temperature, but you still have the same number of molecules. at that particular temperature. Just more of them are at a lower speed than higher speed. And that's what you need to get out of a Maxwell-Boltzmann distribution curve. Yes. Let's talk for a little bit about effusion and diffusion. So diffusion is probably the one that you've heard before. Diffusion is when something spreads from an area of high concentration to an area of lower concentration. And in terms of gases, it's going to be kind of describing how a gas fills up its container. From the area of high concentration, it spreads out into the area of lower concentration until everything is the same concentration. This could be why, you know, if somebody is in your kitchen is making cookies and eventually you smell it in your bedroom, but it's not immediate, it's not instant, because it takes some time for those gas particles to get to your bedroom. Effusion is a little different. It still works on kind of the same idea of diffusion, however, we're going to measure it through a pinhole. I spelled that wrong, through a pinhole. So it's how quickly the gas can escape through a tiny hole in its container. So it's just a way that we measure the rate of diffusion. We just call it effusion. And it's related to the size of the particles. So, you know, if you have a larger particle, increased size, it's going to decrease the rate of effusion. If you have a smaller particle, it will increase the rate of effusion. And for the most part, we use molar mass for this. So if you have something like hydrogen gas is much smaller than something like carbon dioxide gas. Hydrogen gas is going to effuse or diffuse a lot faster than carbon dioxide gas just based on the size. This is also kind of relating back to that kinetic energy example, 1/2 mv squared, because the mass of hydrogen is much lower. If you keep the kinetic energy the same, that means it can have a much higher speed as compared with carbon dioxide. If they have the same kinetic energy, a larger mass, you'd have to have a slower velocity to meet that same kinetic energy. All right, let's say we have three gases, hydrogen gas, hydrogen chloride, and chlorine gas, and they're all at 600 Kelvin, for example. Let's take a look at their average kinetic energy and then their average speed. Because AP likes to ask those two questions. They'll ask you to compare the average kinetic energy between the three and compare the average speed between the three. So the average kinetic energy for all three of them are equal. That's because they're all at the same temperature, and Kelvin temperature is directly proportional to the average kinetic energy. But average speed, because kinetic energy is based both on mass and on velocity, the lightest particle is going to move the fastest, then the medium one, and the heaviest particle will move the slowest at that same temperature. So please make sure that you're keeping kinetic energy and speed separate in your brains.